This is a quick recap on the 5 types of reactions that you probably learned your first year of chemistry. You can see the 5 types of reactions on the left-hand side here real quick. AP really focuses on synthesis and decomposition. Whoa, don't do that. Synthesis and decomposition, which is our top ones here. And a lot on double replacement. They do some on single replacement, which is what we're going to get to with redox, and combustion is always something we've got to look at. So these are the 5 types. Taking a look at them, kind of break them down. Synthesis is the coming together part. You can see that you've got 2 kind of single elements, 2 smaller things. It doesn't have to be elements, it doesn't have to be molecules, it has to be 2 smaller things that combine in some way to be making one larger thing. So simple moving on to complex. Our generic equation for this would be A plus B equals AB. Decomposition is the opposite of that. Start with something that's really complex, like NH3, and break it down to its more simpler parts. Now, it doesn't have to go all the way to just its pure elements, like you can see here, it's diatomic molecules in the pure element form, but it does have to go simpler. So decomposition is the idea that you're going to break it into simpler parts. Single replacement is just like it sounds, or single displacement, whichever way you want to look at it. That's when one part, if you look at this green dot, is going to come in and kick out another part. So the blue one gets kicked out, so it's by itself. It's a single element replacing another one. So here you can see Mg is a single element, and it's going to replace one of these here. We're going to do an example problem with that. Double replacement is the double switcheroo. Double displacement or double replacement. That's when you're going to take, like here, Na is stuck to S, but on the right side, Na isn't stuck to S anymore. Na is now a Cl. It has come in, Na has come in and kicked out the calcium to be hooked up with chlorine now. We're going to do another example of that one too. And the last one is combustion. Combustion is going to be some sort of carbon-hydrogen thing. As you can see here, carbon-hydrogen thing. Sometimes oxygen can be involved, it doesn't have to be. Plus oxygen, and it's always going to make CO2 and H2O. Now the real definition of combustion is that it always has to react with oxygen. Most of the time whenever we're going to see combustion, we're going to be looking at it in the form that I just talked about. So let's look at the stuff on the right-hand side over here. Okay. So first thing I'm going to be able to do is be able to identify what type of reaction it is. So let's do that first. When I look at this first one, I see a compound plus a compound. If you look over here on the right, synthesis includes simple parts. Decomposition, that doesn't work. Single replacement is always an element plus a compound. So double replacement is the only place where you've got compound plus compound. This one is a double replacement reaction. Look at the next one here. I see I have element plus a compound. Go to my list. Synthesis is usually 2 elements. Decomposition is 1 compound on the left. Here is where I have something where I've got a single element plus a compound. This one's a single replacement, or a single displacement. Last one here, I see I got oxygen. Whenever I see oxygen as a reactant, I'm going straight combustion, because that's the definition of it. Combustion it is. And here you can see I have some sort of CHO thing plus oxygen. It's going to make the same products every time. Okay, so let's kind of look at it. I have BaOH2, my double replacement reaction. You want to be able to know how to predict the products of these. So the first thing I like to do is put in my ion charges. Barium is a 2+, hydroxide is a 1-, hydrogen is +1, and nitrate is a 1-. And then the next thing I'm going to do is kind of switch partners. So right now barium is hooked up with hydroxide, but now in a double displacement or double replacement, he is kicking out the hydrogen. So now barium is with nitrate. I'm going to put some brackets around here because barium is a 2+, which I can see right here, and nitrate is 1-, so in order to make this compound balance, I've got to put a 2 there. Plus, so now that that happened, my hydrogen is now hooking up with my OH to make HOH, or in our real world, we'd call that H2O. I'm actually going to write this as HOH just so you can see how I balance it a little bit easier. HOH, H2O, same thing. So first, you have to have balanced compounds. I have an HOH plus 1 minus 1. Barium nitrate plus 2. Now it's a total of -2, so I'm good. And now I can put in the coefficients in the front. So that's where I'm going to look at and see, okay, OHs, I have 2 OHs. OHs, I have 2 OHs. So I'm going to put a 2 in front of here, which creates 2 hydrogens. Oh, I'm going to need 2 hydrogens here. That creates 2 hydrogens, which now gives me 2 nitrates, and I exactly have that. And I have 1 barium on each side. So in this balanced equation, it's a 1, 2, 1, 2. You can leave it like this, or you can stick in some 1s. That's fine too. Moving on to the next one. This one's a single replacement. I know that because it's an element plus a compound. So I like to put in charges. chop this here. Calcium is a 1 plus, and hydroxide is a 1 minus. So in a single replacement, the Al, or whatever element you have to think about what does it like to be. Al likes to be a positive thing, so he's going to kick out the positive guy. If whatever you had here that has the element like to be a negative thing, like a chlorine, then it would be a negative thing and kick out the negative thing. So you have to think about what kind of charge does this guy like to be. Because if he wants to be positive, he'll want to hook up with a negative guy. If he wants to be negative, he'll want to hook up with the positive guy. So keep that in mind. In this case, aluminum, we know aluminum, if he's going to have a charge, he'll have aluminum 3 plus, which means he's going to kick out, in this case, potassium, and he's going to hook up with hydroxide, OH minus. I'll put parentheses around here because I need 3 hydroxides to make that balance. And then what's left all alone is this potassium. So looking at that, I have just potassium going on. Now I got to balance the equation. That means I got to put the big numbers up front. Boop. So I can see I have 1 hydroxide on this side and 3 on this side. So I'm going to need a 3 up front here. That creates 3 potassium, so I'll put a 3 there, and I'm good. I'm balanced. Moving on to our last example. This one is definitely combustion. Combustion reactions, when you've got some sort of C thing plus oxygen, will always make CO2 plus H2O. Every single time. As you can see right here. So now I just got to balance it. It's going to be more of a tricky one, so I'm going to do CHO to show you how I keep the chart. I'm going to kind of count them ahead of time. I've got 5 C's here, 1 C on this side. I have 10 H's on this side, and I have 2 H's on this side. Here I have 1, 2, and 3 oxygens. Here I have 1, 2, and 3. When you're balancing any kind of combustion reaction, you want to start with C's, then do H's, then do O's. So the first thing I'm going to do is put in my C part. I'll put a 5 here. Now I've got 5 C's. Now I'm going to go H's, and then I'll deal with O's. I got 10 H's on the left, so I've got to put a 5 here, because 5 times 2 equals 10. And now I'm actually going to count how many O's I have, because I did add some numbers. 5 times 2 gets me 10, plus, in this case, 5 more. Gives me a total of 15. Okay, so that's a little tricky, because on the left-hand side I have 3, and on the right-hand side I have 15. So here's where I want to say, okay, right here it's got a lot of stuff. If I put a number in this spot, that's going to really screw everything up. So I don't really want to do that unless I have to. So if this is always worth 1, then how can I make this worth 14? Because 1 oxygen from here, 14 oxygens from here, would add up to a total of 15. And then that would be lovely. I can do that. I can put a 7 here. 7 times 2 equals 14. And then this adds up to 15. And everything works out lovely. The last thing I want to talk about in this video is states of matter. So as a reminder, AP will expect you to know certain solubility rules. They're going to expect you to know that all of the sodiums, potassiums, ammoniums, and nitrates are soluble. Any other rule they'll tell you. Any other rule they'll tell you. So that's kind of handy. So if you look at the first one, barium nitrate. As the AP rules say, all nitrates are soluble. This would be aqueous. Water. Water we know to be a liquid. There's my state of matter. You can't have water dissolved in water. That would be a liquid. So water will never be aqueous. Moving to the next one. According to the rules, we don't actually have to know hydroxides. You'd have to look it up. I did look it up. Aluminum hydroxide would be a solid. It makes a precipitate in this case. Potassium is also a solid. 2 precipitates. That makes it tricky. Looking at the bottom part, CO2 we know is a gas, and H2O we know is a liquid. So, balance equations are coming back, and solubility rules are coming back, so we've got to think about things. Do we make a precipitate or do we not? And that'll be in the next video on ionic versus non-ionic. I hope this helped.